Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020, and this is the third continuation of our lecture, A Gentle Introduction to Infinite Series Solutions for Differential Equations. When last I left you, you were trying to work on this problem. I hope you finished it, but if not, you know what to do. Let's see how you did. And by the way, this time we're dealing with a really variable coefficient. Okay, p of x, the coefficient of y double prime, is 1. And so every point is an ordinary point. So we'll start out and do what we did in the first example exactly. And so we compute the first two derivatives. And we plug it into the differential equation. Here was y double prime, here was x times y, and that's equal to 0. But unlike the first example, we need to get all the coefficients moved into the series. And the coefficient is x. And so we move x into the series. We get x in minus 1, and so this is what we have. Now we want to consolidate this, so we have to do some shifting. So we'll shift the first series down by 2, starting at n equals 0. That'll make these numbers go up to keep things balanced. And the second series will be shifted, the exponent we shifted up by 1 to get them both in terms of x n. And so we have this expression. But now we want them to start at the same value of n. Now there's no way for us to fix this, so what we're going to do is we're going to strip out the n equals 0 term from this one, and we'll write it this way. And now we have something where we can actually do some work with this. So let's look at just that. Now don't forget there is the first term that's there, but now we have this, and so we will consolidate that inside the same sum. And now you see for n equals 0 we have that first term, 2a2 is equal to 0, and that means that a2 is going to be 0. But for the others we will have this recursion relationship, and that's going to be equal to 0 for every, for n equal 1, 2, 3, and so on. And I will solve this recursion relationship for n plus 2. And that's what we have. And now we're going to use this recursion relationship to do some calculations. So we'll start plugging some things in. Now, there are a couple of things to note about these coefficients. First of all, every third coefficient is going to be 0 because it's going to take you back to a2. Next, the formulas are not as easy to work with. That happens. And finally, the formula won't work for k equals 0. And so anyway, we will get this, and we have come up with what the general term is. So a sub 3k is going to be this. It is going to be tied to a0, and it's going to be 3k. Actually, it's not 3k factorial because you're skipping some values here. You're skipping 4, I guess. And 3k plus 1 is going to include the other values. So this is what we get, and the third term is going to be 0 every third term. So those are what you get. So we end up with this expression. And if we collect like terms, we can factor out what a0 is, this one, and a1 is this one. Neat, huh? Let's look at another example. Now here I'm changing the directions up a bit. It says find the first 4 terms in each portion of the series about, and now we're doing it about a different point. It is x0 equal minus 2 for this differential equation. Now the differential equation is the same. You know what to do? Let's see how you do. Now unfortunately, changing that point to x equal minus 2 completely changes the problem. So we want to have a solution that looks like this. So the derivatives are going to look like this. So plugging it into the original equation, we get this was y double prime minus x, and this is y, is equal to 0. But look, we can't distribute this x into here because it's not of the form x plus 2. So what we're going to do is that famous mathematical technique of adding 0 in a clever way. And so we're going to now distribute this, the x plus 2, and this is a minus, so that is going to be a plus, and this minus is up here. The signs work out correctly. And so now we have 3 infinite sums that we need to deal with. And what we need to do is, let's see, we shift that in there, we move this in there, and that's all we really did. So now we have this. So we have 3 series to work with, and that will happen in many problems. Now we need to shift the first series down by 2 on the indices, and then we're going to shift these up, and this is what we get for that. And now what we have is x plus 2 everywhere. Except we have a 0 term here and a 0 term here, and all we have is an n equal 1 here. So what we're going to do is we're going to have to strip out these 2 terms, and then we have n equal 1 for all of these. And then what we can do is we can consolidate these. So we have these 2 terms stripped out, but now we go n equal 1 is all of this stuff equal to 0. Now for this to be equal to 0, what we know is that these 2 things have to sum to 0. And we now have a recursion relationship, but look, it is a 2-step recursion because we have a n minus 2 is a n and a n minus 1. So I set this equal to 0 and I solve for the power and I get this. So for n equals 0 I have this relationship. For n equal 1, 2, 3 I have this relationship. And so now I will start substituting things in. But remember, I ask you to only find the first 4 terms, and some of them will involve a 0 and some of them will involve a 2. And so what or a1, excuse me. And so what I'm going to do is I'm going to substitute in and get the calculations. This is for n equal 1. This is for n equal 2. This is for n equal 3. And when we substitute all of those in, we have these expressions. And we collect like terms. And we have, and I guess I said 4 terms for each. So here's a 0, and there is 1, 2, 3, 4, maybe that's 5. And here's a 1, 1, 2, 3, 4. So I guess I have 4 for each, and I actually have 5 for the first one. So you see, this gives us a good approximation because you're probably interested in a point that is close to -2 anyway. And so this is going to be very close to 0, so we can probably stop after we get 5 terms if we wanted to. Let's look at another problem. This might be our last one. I want you to find the first 4 terms in each portion of this series around x0 equals 0 for the following differential equations. But now we have x squared plus 1 minus 4x. So we have that. You know what to do. Let's see how you did. Okay, so this is p of x, and p of x doesn't equal 0, and so that's an ordinary point. So we will take our derivatives and we'll plug them into the equations, and we get this. Now what we're going to do is we're going to distribute this in, and multiply that inside, and we will have to distribute here. So what we get then when we do this is this sum, this sum, this sum, and this sum. Now we need to do some shifting here. We have n equals 0 here, we have n equal 1 here, Those are n equal 2. And so we're going to shift the second series to n equal to 0. And then we're going to shift this one to n equals 0 also. And we're going to collect like terms, and we have xn. And so we're going to be able to simplify that a bit, because we have an and an, so we can simplify those a bit. And we will get this expression. And now we're going to solve this for, we're going to set all the coefficients equal to 0. We're going to solve for the largest one is an plus 1 for n equals 0, 1, 2, and 3. And now what we can do is we can go through and calculate these. But notice that what will happen is for n equal 2 and n equal 3, it will end up being 0, and it's 0 the rest of the way out. So that means when we substitute these values in, we're going to have a finite series, and this is an example of a polynomial kind of problem, and so it's going to be a linear combination of this and this, and those are linearly independent because this only has even powers of x and that has odd powers of x. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other.